Okay, so what is differential calculus? So to put it simply, differential calculus is the study of instantaneous rate of change of a function. So we've got this little description here which says differential calculus is the procedure of finding the instantaneous rate of change of a function. By finding the derivative of a function, we can find the slope at any point. So let's just look at a general scenario of a car traveling at a certain speed over a certain amount of time. So let's just say we had time there and speed there. And let's just say that maybe it looks approximately like this. So it's a constant change in speed where as time goes on, the car gets faster. And let's just say this is given by y equals 2x. But as we all obviously know quite well, that cars don't move in this perfect rate of change as they're driving, and it could possibly look more like this with some bumps and changes as whatever happens, and it can be quite inconsistent. And so the question is, what if we need to find the exact acceleration of the car at, say, a certain point? And we know that in this scenario, s over t, so speed over time gives acceleration. And so what if there was a really effective way that we could actually find the acceleration, or whatever the variables may be, at a certain point just using some simple equations? And so if we look on the graphic we've got on the left here, we can see that in this table here we've got a function, and it's just given by fx, it doesn't have an exact value. And we can see in the red line, that's the tangent, just an example, but it's a tangent that represents the slope at a given point that, let's just say, is there, where the actual tangent touches the graph. So by looking at a tangent at a particular point, we can find the gradient at that point. So this is the rate of change at that particular point. So using methods of differential calculus, we're actually able to find an equation that gives us the rate of change at any point along a graph. So if we look at this section that says example scenarios, so we saw in the example before, and obviously that's right here, that we've got the position, which is just the curve of the graph, is given by just fx. And so what differential calculus does, and this is just a general way of presenting it, is when we find the derivative, so the function that allows us to see the exact rate of change of the function, we present that as f-x. So looking at this, if we had a graph that represented position, then if we were to find its derivative, we'd be looking at its speed, because we know that by using this method, we're looking at the rate of change of position, and we know the rate of change of position is given by speed, and that's what I've got here, change in position. And similarly, f-x, which is called the double derivative, which is basically just taking another derivative of the function we just found, will give us acceleration, which, like speed, this scenario is the change in speed, because we're looking at the rate of change of a particular graph. And so this can be presented in a wide range of forms. You'll see a general form with x squared, or like x to the power of 3 plus 4, or whatever it might be. You'll see the use of exponential and logarithmic functions. And so obviously you can see here I've got examples of what happens when you find, so this is fx, and then you find f-x, so the derivative, and we'll go more into this in a future video. And then you can also see this used for trigonometric functions. So basically, to put it simply, we can use a wide range of differential calculus methods to find the equation of the derivative of a particular equation of a graph that will actually allow us to determine the rate of change of any point on the graph. And using this information, we can start to look into more applications surrounding determining different points on the graph, looking into kinematics, and also areas such as optimization.